Hello everyone, my name is Oliver Thomas. I'm a student here at the University of Sussex's Predictive Analytics Lab, and today I'm presenting work completed with colleagues at Cambridge, which we've called an algorithmic framework for positive action. And I'll just send in the chat a copy of my slides in case anybody wants to follow along at their own pace. So our work incorporates positive action, which is mentioned in UK law under the Equality Act 2010. In the Equality Act, certain characteristics of an individual are protected. These include race, disability, and marital status, amongst others. But what is positive action? Well, it's a series of lawful measures one can take with the aim of tackling underrepresentation. For example, some careers are disproportionately dominated by one gender in comparison to the wider world. Positive action provides a mechanism to begin to address this imbalance under the condition that the actions taken are proportionate to the extent and longevity of the underrepresentation. It's worth mentioning at this point that although I'm speaking about UK law, there are similar notions in the EU and elsewhere. So why are we interested in positive action? Well, addressing underrepresentation isn't going to take a simple solution. There's not going to be a silver bullet. Instead, a concerted effort must be made to ensure a more equitable society. Positive action allows for a series of lawful measures to be taken to encourage and train people from underrepresented groups. The aim isn't to hire or promote unqualified individuals to meet some quota, but rather to help remove barriers in identifying qualified candidates. One limitation, however, as we'll see on the next slide, is that there may be a cost associated with providing positive action. Examples of positive action in practice could include relatively broad strokes, such as holding open days for candidates from underrepresented groups, or using targeted advertising for vacancies. Other examples might be more costly to achieve, such as the highlighted example of offering training or internships. Offering this to all members of an underrepresented group may simply not be feasible. In this paper, we aim to show that incorporating positive action into a decision support system can promote equal representation while respecting anti-discrimination laws. We do this by trying to identify candidates that are the most suitable for positive action. Let's place positive action within the context of algorithmic notions of fairness. Three commonly cited notions of fairness include demographic parity, which is an intuitive measure that assures positive outcome rates are equal across groups that share a protected characteristic. There's equality of opportunity that aims to address some of the practical limitations of demographic parity and assures that true positive outcome rates are equalized across groups that share a protected characteristic. And lastly, we have individual fairness that requires similar individuals to be treated similarly. Although demographic parity is intuitive and immediately challenges the status quo, its blind application may lead to the violation of anti-discriminatory laws. Equality of opportunity and individual fairness, on the other hand, don't have this problem, but they are status quo preserving. There is, of course, a caveat here that as the definition of similar and individual fairness changes, there can be this kind of striking effects on the outcome. So who should these positive action outcomes be presented to? And why do we need an algorithmic approach? This gets to the aim of our paper. We assume an already existing system that supports the decision-making process. A naive approach might be simply to take the top candidates from an underrepresented group that were ultimately rejected. While this can work with a calibrated data set and a precise model, this can easily fail in complex scenarios such as recruitment, where the concept of a great employee, or in academia, admissions, where the concept of a great student is hard to truly characterize. Take this toy example. Consider a minority who traditionally send their children to schools that teach English to a good level but teaches maths only to a basic level. And suppose this minority is underrepresented within STEM subjects. To keep this example simple, we consider that the application consists of grades in only two subjects, maths and English, with equal weight. In the eyes of a model, that places equal weight on English and maths performance. Both candidates A and B from the underrepresented demographic, which is shown on the second row, obtain an equal score. So who should be identified? Considering maths grades are systematically lower, we ask what might the grades have looked like if the distribution was rescaled to be that of the majority. In doing this, we discover that candidate B actually did rather well. So I should stress that in our approach, this recalibration is only put into effect when populating the group of positive action candidates. When applicants are considered for acceptance, the features are taken as they are. In the case of this example, we're still unable to accept applicant B as they are. They were rejected after all, but they can be flagged for positive action. A maths foundation course, for example, is likely to allow them to be successful in a subsequent selection process. Performing this calibration isn't difficult in a simple example, but when we use more complex features, this method becomes infeasible. It's useful at this point to take an aside into algorithmic fairness, which is kind of where my headspace is most of the time. Let there be some features X, an output variable Y, and a protected characteristic S. Typically, in machine learning, we assume a relationship. We try to model between X and Y, shown by the green arrow. The fairness community has highlighted that these decisions don't exist in isolation. A protected characteristic can influence both the features and the outcome directly. These are modeled by the blue and the red lines respectively. In our approach, we aim to find candidates affected by this blue pathway and remedy decisions that are seemingly affected by the red pathway, which captures direct discrimination. To do this, we conceptually separate S into two independent variables to try and determine the effect of each. Our aim is to interrogate the system to identify two broad sources of discriminatory behavior, those that manifest in the features and those that manifest as directly discriminatory patterns. In our approach, we try to find a mapping between under and overrepresented groups to create counterfactual examples. A counterfactual being a non-existent sample, but one that reflects our understanding of the changes that would have occurred to a sample prior to the data capture, had the steps leading up to that point been different. We then compare the outcomes across counterfactuals to determine discrepancies in outcome, which we try to demonstrate on this rather busy slide that I'm very sorry about. There's three things next to each other. So on the left is a reminder of the conceptual distinction. In the middle is an example that I'll walk you through, and on the right is a set of decision rules that we'll come to shortly. So in the middle, a candidate is considered for a role. We borrow from fair representation learning literature and train a model to produce a latent representation Z, which contains information about an individual independent to S. We then use this to generate a counterfactual version of them. That is, we generate a counterfactual in feature space. We then append all values of the protected characteristic to allow a shortcut for a potentially biased decision-making system. For a protected attribute with binary values, this produces 4 counterfactual samples. These are then fed into the decision support system, giving us an array, in this case, of 4 outcomes. We then use decision rules, shown on the right-hand side, to analyze the array of results per individual. These should, of course, be obtained in conjunction with a domain expert. In the case that there's an agreement in the outcomes across all counterfactuals, then we go with the consensus decision. Where there is disagreement due to direct discrimination, we take the outcome most favorable to the applicant. And in the case that there's disagreement due to the effect of a protected characteristic on the feature space, then there are 2 possible outcomes. If the real applicant would have been rejected, but their counterfactual version belonging to a majority group would have been accepted, then they're flagged as a positive action candidate. We can't accept them, but there may be additional outcomes that would be more suitable. In the case that the real applicant is accepted, but their counterfactual version wouldn't have been, then they're still accepted, as our aim isn't to punish applicants, but solely to highlight promising candidates and provide feedback to a system designer. And so at this point, just to answer one of the reviewers directly, this may seem similar to deferral or rejection modeling, where there's an additional outcome, where there's also an additional outcome. In these methods, if the outcome of a model falls within an uncertain range, as I've attempted to show on the left-hand side of the slide, the decision is deferred to either an expert system or a domain expert. However, a model might be completely certain, but for reasons influenced by a protected characteristic. On the right-hand side, I've tried to demonstrate a situation where our counterfactual modeling approach would succeed in identifying uncertainty with respect to a protected characteristic, but a deferral approach wouldn't. Here the model is always entirely certain the outcome, but for reasons influenced by a protected characteristic. So in our experiments, we use both synthetic and real data to evaluate our model, though here I'm only going to talk about the synthetic one. Please feel free to read the paper for more details on the real data. The advantage of using synthetic data is just that we can access additional information, such as what a ground truth counterfactual would have been that's practically impossible to get in the real world, and any subsequent outcomes, which is kind of useful for our synthetic setup that I'll explain in a moment. So in the synthetic data, we're modeling a admissions scenario for a university with biased past behavior affecting two subgroups, the blues and the greens. And there's a continuous set of input features representing examination scores. And the task is to emulate the process of determining who should be admitted based on past decisions. In addition, we've got an unseen outcome of a variable that identifies for all students whether they were accepted or not, whether they would have indeed gone on to graduate with a good grade based on their inherent characteristics. We compare our approach against the demographic parity oracle, an unconstrained logistic regression model, and FairLearn, a package implementing Agarwal et al.'s a reductions approach to pair classification. And although there's a lot of numbers on this table, I kind of want to highlight two results. The acceptance rate, which demonstrates kind of the light touch of our approach, showing that our model is similar to that of an unconstrained baseline. Here I just kind of want to emphasize that our approach retains accuracy. I also want to highlight the TCP, or true capture percentage, and this is an unusual metric that I don't expect anybody to have come across before, for two reasons. First, we treat positive action candidates as receiving a not reject outcome, so accept, I guess. And secondly, because we condition on whether the applicant would have indeed gone on to graduate. Here our approach not only does very well at identifying candidates that go on to do well, but it's also well balanced between the protected groups, blue and green, or B and G in this case. So just bring this towards a close. I just want to highlight some limitations and future directions. One of the limitations of this, as far as we're aware, this is the first kind of work where we're talking about positive actions in an algorithmic setting. And because of that, we've only considered a binary protected groups, which is in line with work from algorithmic fairness literature, although obviously in the real world, you're going to deal with more than binary protected groups. So that's certainly one limitation of our work. We've also produced hand-determined rules about who should be accepted and not based on this array of outcomes that are produced, and that may not be generally applicable. Also, because we're dealing with counterfactual modeling, it's particularly hard to evaluate. And that's a limitation that with similar works have faced. In terms of future directions, we're really interested in characterizing the uncertainty over these generated counterfactuals to try and understand how much faith we could really put into them, and considering more complex scenarios. Also, given that part of the motivation is around the cost of more expensive positive action measures, incorporating some kind of budget would be particularly useful. So, as a conclusion, positive action as an additional outcome is a method to increase equal representation over time. Please consider it. And we've presented an approach based on counterfactual modeling that tries to identify positive action candidates while mitigating directly discriminatory behavior. Thank you very much.